Over a single 48-hour window, roughly 1.5 million active users severed their ties with ChatGPT, routing their daily workflows toward Claude. This migration followed a stark divergence in corporate policy. While OpenAI absorbed a canceled U.S. military contract, Anthropic publicly rejected the deal, positioning themselves as a privacy-focused alternative to mass surveillance. That policy shift created the initial intent to switch, but a significant technical hurdle remained. Users had spent months training OpenAI's models on their specific needs, and they were reluctant to lose that stored context. This is the memory moat. An LLM accumulates a dense history of your specific workflows, formatting preferences, and instructions. This data is stored in a proprietary database, creating high friction for any user attempting to move to a different provider. To facilitate the 1.5 million user exodus, Anthropic engineered a specialized text prompt. This linguistic tool was designed to command OpenAI's own system to package and export the user's historical context data in a portable format. This technical exploit neutralized OpenAI's strongest retention mechanism, allowing users to carry their personalized workflows with them to a new platform. At a technical level, LLM memory aggregates user constraints into a unified context profile. This profile resides outside the chat window. When you submit a query, the system retrieves data from this profile and injects it into your prompt. This allows for hyper-personalized outputs. The model knows your preferred tone, your coding style, and your specific formatting requirements without needing a new set of instructions for every chat. Refining this profile requires a significant time investment. It takes months of active daily tuning for the system to accurately predict and apply a user's specific operational constraints. This investment makes switching platforms a costly endeavor for the consumer. This dynamic functions as a retention moat. Users often remain with a platform they no longer trust because they want to avoid the friction of retraining a new model from a blank slate. Anthropic identified this specific data silo as the primary obstacle preventing users from moving their workflows to Claude. Success in the market required more than model parity. Anthropic needed a way to make this historical context data portable. Anthropic bypassed additional security barriers by using natural language to command a data export. They wrote instructions designed to make the competitor's system retrieve and display its own internal memory logs. The vehicle for this exfiltration was a highly calibrated block of text, the extraction prompt. This context transforms a generic tool into a bespoke system. In a competitive landscape, the user's accrued historical data is the most valuable asset in the AI stack. Anthropic provided prospective users with a specific prompt layout. The text uses imperative commands, extract, summarize, and compile to target the system's underlying data layer. This isn't a standard conversational query. It is an internal query command that forces the AI to look at its own hidden system instructions rather than the user's current query. The architecture of the prompt is designed to bypass standard chat guardrails, triggering a comprehensive dump of the user's hidden context profile. To execute the exploit, users pasted this payload directly into the ChatGPT interface. ChatGPT processed the command without resistance. It retrieved the user's preferences and output them as a structured, portable data block. This frictionless output effectively drained the value from OpenAI's retention mode. The data shows a massive shift in the user base. Roughly 1.5 million active users moved away from ChatGPT during this window. This mass departure occurred in a 48-hour period, marking an exceptionally fast transition for a high-retention software category. As ChatGPT's user numbers fell, Anthropic saw a corresponding surge, gaining 1 million daily subscribers. Users took that extracted data block and pasted it into Claude's memory settings, gaining personalized day-one performance without manual retraining. By complying with the user's extraction command, ChatGPT provided the very data required to facilitate its own user's departure. This exploit was not limited to OpenAI. Gemini users were also part of this migration wave. Google faced the same threat. Users attempted to apply the Anthropic extraction method to Gemini to move their data into the Claude ecosystem. This allows for an A/B comparison of how different system architectures handle the same payload. When the Anthropic extraction instructions are entered into the Google Gemini interface, the outcome changes. Gemini returns a hard error, stating that no stored instructions or data were found. This response indicates a specific architectural barrier designed to identify and block context exfiltration. Google's defense relies on a process called defensive prompt filtering. This system-level guardrail analyzes the intent of the input. It searches for commands related to memory extraction or context porting before the language model generates a reply. If the filter detects a request for the context profile, it intercepts the command and generates a null response, preventing the data dump. Where ChatGPT complied with the command, Gemini's architecture actively refused to provide the necessary data for a competitor's onboarding tool. By blocking the prompt, Gemini kept the user's context profile within the Google ecosystem, maintaining high switching costs. Google identified prompt injection as a strategic business risk and deployed filters to prevent user context from becoming portable. This event illustrates a shift in the macroeconomic reality for the top 3 LLM platforms. As the technical capabilities of these AI models equalize, raw performance metrics are losing their relevance as the primary driver for user acquisition. User context data has become the most critical competitive moat in the AI space. Anthropic has demonstrated how prompt engineering can be used for mass data exfiltration, while Google has shown that system-level filters can stop it. Systems engineers and product managers should test this. Run the extraction prompt across different enterprise tiers of Gemini and ChatGPT to document the current state of defensive filtering. Future market dominance will be determined by those who can engineer context portability exploits and those who can build the walls to stop them. Anthropic recently launched a targeted strategy to capture users from OpenAI and Google, distributing a custom-engineered prompt designed to break platform lock-in. The prompt serves a specific technical function. It instructs a model to query its own conversational history and format that data into a portable summary for migration into Claude. Testing this on ChatGPT yields a compliant response. The model summarizes the user's preferences and past interactions, effectively exporting its internal memory. The results change when we deploy the identical prompt on Google's Gemini Pro. While ChatGPT exports the data, the input on Gemini hits a hard barrier and fails. Across multiple Pro accounts, Gemini returns the same specific error string, no stored instruction found. Because large language models are probabilistic, returning a static, identical error message across different accounts suggests a systemic intervention rather than a standard model hallucination. These platforms are shifting away from neutral text generation and toward the architecture of defended walled gardens. Gemini's specific error is our entry point to reverse engineering the contextual moat, the semantic guardrails platforms now use to prevent data migration. Within LLM architecture, memory is a computationally expensive dataset that tracks highly personalized user patterns over time. One method for retaining this memory involves updating the hidden system prompt. Here, months of chat history are mathematically compressed into code that guides every future response. A more robust method links a dedicated vector database to the user's ID using retrieval augmented generation, or RAG. This database operates in the background, indexing every instruction and preference to provide a consistent experience across sessions. Every time you type a query, your input merges with a massive flow of data from this database before the combined request reaches the core model. Rebuilding this optimized parameter space on a new platform requires months of active use, creating significant friction for any user considering a move. This friction forms a contextual retention moat, making the cost of migration higher than the benefit of a slightly better model. Anthropic's extraction prompt was engineered to bypass this retention friction by forcing the model to reveal its own hidden context. This is a form of benign prompt injection. The input isn't looking for a creative answer. It is designed to manipulate the system's operational parameters. The prompt contains an instruction that targets the model's internal layers, curving backward to query the hidden system prompt and RAG data directly. It demands that the model output a condensed, portable summary of these hidden preferences, turning internal memory into a text file. When ChatGPT receives this vector, its internal pipeline processes the instruction like any other request. Because ChatGPT treats the instruction neutrally, the model proceeds with the request without identifying it as a data exfiltration attempt. The system accesses its contextual history, generates the summary, and delivers the data to the user without triggering any internal alarms. Treating all prompts with the same neutrality leaves these models vulnerable to engineered exfiltration of their most valuable data. Gemini's failure and the "no stored instruction found" error provide evidence of a more aggressive defensive posture. If the core model had generated this refusal, we would see conversational variation. Instead, the rigid syntax indicates that the prompt was intercepted before it reached the inference stage. This architecture places a semantic router or intent classifier in the input pipeline. The user input hits a routing gateway before it ever touches the massive core model parameters. This gateway analyzes the linguistic signature of every prompt to determine its intent before allowing it to proceed. Google's router identified the fingerprint of Anthropic's migration prompt. The gateway flashes as it recognizes the intent and immediately diverted the input onto a secondary path. This router-level interception overrides the core model entirely, ensuring the prompt never interacts with the model's parameters. The diverted path hits a dead-end block. The system returns a static, pre-programmed error string rather than a generated response, successfully blocking the extraction attempt. Through this hard-coded API routing intervention, Gemini successfully defends its contextual moat against competitor exfiltration. In consumer-facing interfaces, large language models are increasingly encased in defensive infrastructure. Direct neutral access to raw parameters is being replaced by highly mediated systems. The Anthropic Gemini incident proves that platforms are now deploying adversarial input filtering to actively block each other. Prompt engineering has evolved into an offensive mechanism used to probe these systems and force the export of locked-in data. This is the modern closed ecosystem stack: the user interface, the defensive routing layer, the core model, and finally, a defensive output layer. For those building integrations, understanding this four-layer stack single token of inference occurs. In the current AI platform landscape, competitive advantage is determined as much by the defensive architecture of the routing layer as by the intelligence of the model itself.